Some machines are built to work, others are built to last, and a rare few are built with the understanding that once they start, they may never be allowed to stop. Hidden inside dams, buried underground, stretching across deserts, or operating quietly behind concrete walls, these machines have been running for decades, often longer than the people who designed them ever imagined. They do not rest. They are maintained while moving, repaired while operating, and upgraded without shutting down. If they stop, entire systems fail, cities lose power, industries collapse, or disasters unfold. This is not a story about speed or innovation. It is about endurance, about machines pushed beyond normal limits and kept alive through discipline, engineering, and necessity. These are 12 of the most extreme examples ever built. Machines that have worked non-stop for over 50 years, and in some cases, far longer. Hoover Dam Powerhouse Turbines, the machines that have never truly stopped spinning since 1936. When the turbines inside Hoover Dam began operating in 1936, they were designed as permanent infrastructure rather than temporary machinery. These hydroelectric turbines were expected to run continuously, delivering reliable power while also supporting flood control, irrigation, and regional stability. From the beginning, engineers understood that stopping the system entirely would never be practical. As a result, the powerhouse was built around redundancy, durability, and a maintenance philosophy focused on continuity rather than replacement. Each turbine was constructed using conservative engineering principles common in the early 20th century. The machines rotate at relatively low speeds, which reduces mechanical stress and limits heat buildup over long operating periods. Their massive size was intentional. Heavy components dampen vibration and allow smoother rotation under constant hydraulic pressure. Instead of chasing maximum efficiency, the designers prioritized predictability and endurance, qualities that proved essential for machines expected to operate for decades without interruption. Water from Lake Mead flows through large steel penstocks and strikes the turbine blades with controlled force. This rotational energy is transferred to generators that produce electricity for the American Southwest. This basic process has remained unchanged for nearly 90 years. While individual turbine units are periodically taken offline for inspection or repair, the powerhouse itself has never experienced a complete shutdown. Power generation continues while maintenance is carried out in stages. Maintenance strategy explains much of the turbine's longevity. Engineers do not replace entire machines. Instead, they refurbish components gradually. Bearings are swapped, shafts are realigned, seals are replaced, and blade surfaces are restored. Sediment carried by the Colorado River slowly erodes turbine components, but redesigned blades and modern alloys reduce damage without altering the original mechanical layout. This approach allows the turbines to evolve while maintaining continuous operation. Modern technology has been integrated carefully over time. Early analog systems have been replaced with digital controls and sensors that monitor vibration, temperature, efficiency, and load in real time. These upgrades improve safety and output without requiring shutdowns. The turbines may look similar to their 1930s counterparts, but their monitoring systems reflect contemporary engineering standards. The importance of these turbines makes stopping them unacceptable. Hoover Dam supplies electricity to millions of people in Nevada, Arizona, and California. It also plays a central role in water management across the region. A full shutdown would disrupt power grids, water delivery systems, and economic activity. Every maintenance decision is therefore planned around continuous operation. The turbines inside Hoover Dam are not remarkable because they are old. They are remarkable because they were built to last, maintained with discipline, and never allowed to stop. Their survival also reflects a period when engineers assumed responsibility for future generations. Every design choice accounted for wear, repair, and long-term access. These turbines were not disposable machines. They were commitments, built with the understanding that someone, decades later, would still depend on them daily. That responsibility remains visible every time the generators continue turning. Fairbanks, Morse opposed piston. Diesel engines, built before World War II, still running today. Fairbanks, Morse opposed piston diesel engines were designed in the early 20th century to solve one problem above all others: how to run reliably without stopping in remote, high-risk environments. They entered service long before World War II, powering submarines, naval vessels, factories, and isolated power stations where failure was not an option. Unlike conventional diesel engines, the opposed piston design eliminated cylinder heads, reducing heat loss, mechanical complexity, and long-term wear. Each cylinder contains two pistons moving toward each other, creating combustion in the center and balancing forces naturally during operation. This configuration allowed the engines to run cooler and smoother than many later designs, a critical advantage for continuous use. Fairbanks Morse built these engines to operate for months or even years with scheduled maintenance performed while the engine remained active. In submarines, shutting down propulsion or electrical generation could mean detection, mission failure, or loss of life. The engines therefore had to be predictable, repairable, and tolerant of abuse under extreme conditions. That requirement shaped everything from material selection to lubrication systems and access points for repairs. Many of these engines remained in service long after newer technologies appeared, simply because they worked. Operators trusted them, mechanics understood them, and spare parts could be fabricated even decades after original production. Stationary versions of the engines powered hospitals, factories, and emergency systems that could not afford downtime. In many locations, they became the backbone of local infrastructure, quietly running while entire communities depended on their output. Over time, components were upgraded, control systems modernized, and fuels adapted, but the core mechanical design remained unchanged. Some engines built before the war are still operating today, either in original roles or as backup systems. Their continued use is not nostalgia, but a reflection of engineering priorities that valued longevity over efficiency. These engines were designed to be understood by human hands, not sealed away as disposable units. When maintained properly, they demonstrated that mechanical simplicity and robustness could outperform complexity over time. The Fairbanks Morse opposed piston diesel engines represent an era when machines were built with the assumption they would outlive their builders. Their survival into the present day proves that constant operation is possible when durability, maintenance, and respect for engineering limits are treated as non-negotiable requirements. This philosophy explains why some units remain operational today, still starting, running, and carrying load without hesitation. They are maintained not as relics, but as working machines trusted to perform when modern systems fail. In an age of rapid replacement, their continued service stands as evidence that endurance can still be engineered deliberately. These engines did not survive by chance, but because they were designed, operated, and respected as long-term assets. Their ongoing operation closes the gap between past and present, proving that some machines truly were built to last. That legacy continues wherever one of these engines is still turning today. It is a reminder that reliability is not outdated, but rare. And when reliability matters most, these engines remain ready, even after decades of service. POSCO Number 1. Blast Furnace, the steelmaking monster that cannot be turned off. POSCO Number 1. Blast furnace was built with a single purpose: to operate continuously as the core of an industrial steelmaking system that does not tolerate interruption. From the moment it was ignited, the furnace was designed to remain active for decades, producing molten iron without a true shutdown. In blast furnace engineering, stopping the process is not a pause, but a failure, because once molten iron cools and solidifies inside the furnace, the entire structure can be permanently damaged. A blast furnace operates by combining iron ore, coke, and limestone under extreme heat. Temperatures inside the furnace reach levels high enough to melt iron continuously, day and night. Once this process begins, the internal lining, known as refractory brick, must remain hot at all times. Cooling causes cracking, deformation, and structural collapse. For this reason, POSCO No. 1 blast furnace was designed to stay active through years of uninterrupted production cycles. The furnace is charged from the top and tapped from the bottom, allowing molten iron to be drawn out while new material is added above. This balance is carefully controlled. Operators adjust airflow, pressure, and material ratios constantly to maintain stability. Even small deviations can disrupt the chemical reactions inside. Because of this, the furnace is monitored continuously by teams of engineers who treat it as a living system rather than a simple machine. Maintenance does not mean shutdown. Instead, repairs are performed while the furnace remains operational. Sections are reinforced, sensors replaced, and cooling systems upgraded without stopping production. Periodic relining occurs only after long campaigns that can last many years, and even then, the shutdown is planned as a major industrial event. Restarting a blast furnace is costly, risky, and time-consuming, which is why continuous operation is always preferred. POSCO No. 1 blast furnace became a symbol of South Korea's industrial rise. It supported shipbuilding, construction, automotive manufacturing, and national infrastructure. Entire supply chains depend on its output. If the furnace stops unexpectedly, downstream industries suffer immediate consequences. This economic pressure reinforces the requirement that the furnace must remain active under almost all circumstances. The furnace's longevity is the result of conservative engineering and disciplined operation. Materials were selected for endurance rather than cost savings. Redundancy was built into cooling systems and air supply networks. Human oversight remains critical, even with automation. Experienced operators understand the sound, vibration, and behavior of the furnace, allowing them to respond before problems escalate. What makes POSCO No. 1 blast furnace exceptional is not its size, but its inability to rest. It cannot be turned off without risk of destruction. Its continued operation represents industrial commitment on a generational scale. This furnace is not simply a machine that makes steel. It is an ongoing process that must be sustained, protected, and respected every hour it remains active. Clair Refinery, crude distillation unit, the heart of an oil giant that runs day and night. Clair Refinery's crude distillation unit is the central system that allows the entire facility to function. Built to operate continuously, it separates raw crude oil into usable fractions that feed every downstream process. From the moment it is started, the unit is expected to run without interruption at all times. Crude distillation is the first and most critical stage of refining. Heated crude oil enters a tall distillation column where rising vapors separate by boiling point. Each fraction is drawn off continuously, forming the foundation for fuels, chemicals, and industrial products used across transportation, energy, manufacturing, and modern global economies. The unit cannot simply be shut down at will. Cooling the system causes internal fouling, metal stress, and dangerous pressure imbalances. Restarting requires weeks of preparation and enormous cost, which is why operators design maintenance schedules around non-stop operation to avoid damage, delays, financial losses, safety risks, and supply disruptions. Clair Refinery was engineered with redundancy to support this requirement. Pumps, heaters, and control systems have backups that can be activated instantly. If one component fails, another takes over, allowing crude processing to continue without halting the unit and protecting downstream systems, workers, storage, logistics, contracts, schedules, markets, output, commitments. Operators monitor the distillation unit around the clock. Temperatures, pressures, and flow rates are adjusted constantly to maintain equilibrium. Small deviations can escalate quickly, making human oversight and experience as important as automation within this environment, especially during feedstock changes, weather events, equipment wear, alarms, transitions, startups, upsets, inspections, emergencies. Over decades of operation, the unit has undergone upgrades without losing continuity. Analog controls were replaced by digital systems, sensors were improved, and materials were strengthened. These changes extended lifespan while preserving the original process design and ensuring compatibility with existing infrastructure, safety standards, regulations, operators' procedures, documentation, training, protocols. The distillation unit feeds nearly every other section of the refinery. If it stops, secondary units lose input and production collapses. This dependency makes the unit the operational heart of the entire complex, supporting fuels, lubricants, petrochemicals, exports, reserves, pipelines, terminals, shipping, storage, contracts, supply, stability, employment, revenue, planning, continuity. Continuous operation also improves efficiency and safety. Stable temperatures reduce stress on metal surfaces and minimize corrosion. Frequent shutdowns increase failure risk, making constant operation the safer option over long time frames for personnel, equipment, environment, emissions, controls, inspections, compliance, audits, reporting, reliability, insurance, response, training, coordination, planning, resilience, consistency, performance. The crude distillation unit represents a philosophy of industrial permanence. It is not treated as disposable machinery, but as infrastructure that must endure. Every decision prioritizes longevity, predictability, and uninterrupted service across decades, generations, market cycles, demand shifts, policy changes, ownership, upgrades, inspections, repairs, staffing, economics, crises, disruptions, uncertainty, risk. At Clare Refinery, the distillation unit defines what non-stop operation truly means. Its survival depends on discipline, planning, and respect for limits. As long as oil flows, the unit is expected to keep running without pause. Interruption, failure, compromise, hesitation, shutdown, retreat, relief, rest, silence, downtime, exception, replacement, redesign, retirement. Boux-Cray Phosphate Conveyor Belt, the longest machine on Earth that never sleeps. The Boux-Cray Phosphate Conveyor Belt is not a single machine in the traditional sense, but a continuous mechanical system stretching more than 90 kilometers across the desert of Western Sahara. From the moment it was completed in the early 1970s, it was designed to operate without rest, moving phosphate rock from the Boux-Cray mine directly to the coast for export. Unlike vehicles or ships that come and go, this conveyor exists for one purpose only: to keep moving material day and night, year after year. Phosphate mining at Boux-Cray depends entirely on this conveyor system. Trucks or trains would be inefficient and costly over such distance and terrain. The conveyor belt solves this by functioning as a permanent transport corridor. Crushed phosphate is loaded at the mine and carried across barren desert to the port facilities, where it is transferred directly to ships. Once material enters the system, it does not stop until it reaches the ocean. The scale of the conveyor creates unique engineering challenges. Wind, sand, heat, and mechanical wear act constantly on every component. Rollers, motors, belts, and supports are exposed to extreme conditions that would destroy ordinary machinery within years. To survive, the system was engineered with redundancy, modular components, and continuous monitoring. Individual sections can be repaired or replaced while the rest of the conveyor remains operational. Stopping the conveyor entirely is avoided whenever possible. A full shutdown disrupts mining operations, port logistics, shipping schedules, and international supply contracts. Phosphate is a critical resource used in fertilizer production, and interruptions can affect agricultural markets far beyond the region. For this reason, maintenance is conducted in segments, keeping material flowing even during repairs. The conveyor belt is powered by multiple drive stations distributed along its length. This prevents excessive strain on any single motor and allows operators to isolate issues quickly. Sensors monitor belt alignment, speed, tension, and temperature. When problems arise, crews respond immediately, often working in remote desert sections far from infrastructure. The system also demonstrates how industrial machines can shape geography. From space, the Bu Cray conveyor is visible as a thin line cutting across the desert. It is one of the most recognizable industrial structures on Earth, not because of its height or mass, but because of its length and permanence. Few machines leave such a visible imprint on the landscape. What makes the Bu Cray conveyor exceptional is not just that it is long, but that it never sleeps. While ships dock and depart and mines pause operations, the conveyor continues to move. Its operation represents a commitment to continuous industrial flow, where stopping is considered failure rather than rest. Decades after its construction, the conveyor remains in use because no alternative has proven more reliable. It operates quietly, mechanically, and relentlessly. The Bu Cray phosphate conveyor belt stands as a reminder that some of the most important machines in the world are not dramatic or fast, but constant. Its endurance defines its importance. Bagger 293 bucket wheel excavator, the land machine that eats the earth, non-stop. Bagger 293 was built to solve a single problem at an almost unimaginable scale: how to remove enormous volumes of earth continuously without stopping. Designed as a permanent mining machine rather than a vehicle, it was never intended to operate in short shifts or seasonal cycles. From the beginning, the excavator was expected to function for decades, moving material every day as long as the mine remained active. Operating in large open-pit lignite mines, Bagger 293 removes overburden so coal can be accessed below. The machine is massive in size, standing taller than many buildings and stretching hundreds of meters in length, yet it moves slowly and deliberately. Speed is not its purpose. Its role is stability and constant output, allowing mining operations to proceed without interruption or delay. At the front of the machine is its defining component, the bucket wheel. This rotating steel wheel holds multiple buckets that cut directly into soil and rock. As the wheel turns, each bucket scoops material and deposits it onto internal conveyor belts. These conveyors transfer the earth away from the excavation site in a continuous stream, keeping the machine moving forward without pauses. Stopping Bagger 293 entirely is avoided whenever possible. A full shutdown disrupts the mine's production chain and creates mechanical stress across interconnected systems. Instead, maintenance is planned in stages. Individual components are serviced while the machine remains partially active, preserving overall continuity. This approach reflects how deeply non-stop operation is embedded in its design philosophy. The excavator does not work alone. It is part of a synchronized mining system that includes conveyor networks, spreaders, and power infrastructure. If Bagger 293 stops, downstream equipment becomes idle. This dependency makes reliability more valuable than raw performance. The entire system is built around keeping material flowing at all times. Bagger 293 is electrically powered, drawing energy directly from external sources rather than carrying fuel. This allows uninterrupted operation without refueling and reduces mechanical complexity. Sensors monitor vibration, load, temperature, and structural stress continuously, allowing operators to identify issues before they become failures. Despite automation, human oversight remains essential. Operators adjust cutting angles, monitor ground conditions, and respond to changes in soil density. Experience matters because incorrect operation can damage the machine or reduce efficiency. The excavator responds slowly, but mistakes have long-term consequences. Over the years, the machine has been upgraded without altering its core structure. Control systems were modernized, components reinforced, and monitoring improved. These changes extended operational life while preserving the original design. Replacement was never the goal, endurance was. Bagger 293 is exceptional not because it is fast or flexible, but because it never stops. It exists to remove earth continuously, supporting energy systems that depend on constant supply. Its steady movement represents industrial endurance at the largest Krupp bucket wheel excavators of Hambach Mine, the giants that have moved mountains for decades. Bagger 293 was built to solve a single problem at an almost unimaginable scale: how to remove enormous volumes of earth continuously without stopping. Designed as a permanent mining machine rather than a vehicle, it was never intended to operate in short shifts or seasonal cycles. From the beginning, the excavator was expected to function for decades, moving material every day as long as the mine remained active. Operating in large open-pit lignite mines, Bagger 293 removes overburden so coal can be accessed below. The machine is massive in size, standing taller than many buildings and stretching hundreds of meters in length, yet it moves slowly and deliberately. Speed is not its purpose. Its role is stability and constant output, allowing mining operations to proceed without interruption or delay. At the front of the machine is its defining component, the bucket wheel. This rotating steel wheel holds multiple buckets that cut directly into soil and rock. As the wheel turns, each bucket scoops material and deposits it onto internal conveyor belts. These conveyors transfer the earth away from the excavation site in a continuous stream, keeping the machine moving forward without pauses. Stopping Bagger 293 entirely is avoided whenever possible. A full shutdown disrupts the mine's production chain and creates mechanical stress across interconnected systems. Instead, maintenance is planned in stages. Individual components are serviced while the machine remains partially active, preserving overall continuity. This approach reflects how deeply non-stop operation is embedded in its design philosophy. It is part of a synchronized mining system that includes conveyor networks, spreaders, and power infrastructure. If Bagger 293 stops, downstream equipment becomes idle. This dependency makes reliability more valuable than raw performance. The entire system is built around keeping material flowing at all times. Bagger 293 is electrically powered, drawing energy directly from external sources rather than carrying fuel. This allows uninterrupted operation without refueling and reduces mechanical complexity. Sensors monitor vibration, load, temperature, and structural stress continuously, allowing operators to identify issues before they become failures. Despite automation, human oversight remains essential. Operators adjust cutting angles, monitor ground conditions, and respond to changes in soil density. Experience matters because incorrect operation can damage the machine or reduce efficiency. The excavator responds slowly, but mistakes have long-term consequences. Over the years, the machine has been upgraded without altering its core structure. Control systems were modernized, components reinforced, and monitoring improved. These changes extended operational life while preserving the original design. Replacement was never the goal, endurance was. Bagger 293 is exceptional, not because it is fast or flexible, but because it never stops. It exists to remove Earth continuously, supporting energy systems that depend on constant supply. Its steady movement represents industrial endurance at the largest possible scale. 3 Gorges Dam, Francis turbines, powering a nation without rest. The Francis turbines installed at Three Gorges Dam were designed to operate as permanent national infrastructure, not as machines that cycle on and off. From the moment the first units entered service, they were expected to run continuously, converting the force of the Yangtze River into electrical power on an unprecedented scale. These turbines form the core of the world's largest hydroelectric project and were built with endurance as a primary requirement. Each Francis turbine at Three Gorges is enormous, engineered to handle massive volumes of water under controlled pressure. Water flows through the spiral casing, strikes the turbine blades, and transfers energy to the generator shaft in a steady, regulated motion. This process repeats every second of every day. Unlike thermal power plants that rely on fuel delivery and combustion cycles, these turbines depend on constant river flow, making uninterrupted operation both practical and necessary. Stopping a turbine is avoided whenever possible. A shutdown disrupts power supply, stresses mechanical components, and affects grid stability across large regions. Instead, the dam operates on a unit-based maintenance system. Individual turbines are taken offline for inspection or refurbishment, while others continue producing electricity. The facility as a whole never truly rests. maintaining continuous generation even during maintenance periods. Durability was built into every aspect of the turbine design. Components were oversized, materials were selected for long-term resistance to erosion, and tolerances were engineered conservatively. Sediment carried by the Yangtze River poses a constant threat to turbine blades, gradually wearing surfaces over time. Engineers address this through advanced coatings, redesigned blade profiles, and continuous monitoring rather than full system shutdowns. Automation plays a central role in sustaining non-stop operation. Sensors track temperature, vibration, water pressure, and rotational speed in real time. Control systems adjust blade angles and flow rates automatically to maintain optimal performance. Despite this automation, human oversight remains essential. Operators monitor trends, interpret data, and intervene when conditions change unexpectedly. The turbines also support more than electricity generation. Their operation stabilizes the power grid, reduces reliance on fossil fuels, and supports flood control and navigation along the Yangtze. This multi-role importance reinforces the requirement for continuous operation. A prolonged shutdown would affect industry, transportation, and regional safety. Over time, the turbines have undergone upgrades without altering their fundamental role. Control software has been refined, materials improved, and monitoring systems expanded. These changes extend service life while preserving operational continuity. Replacement is planned decades in advance, not as an emergency response. The Francis turbines at Three Gorges Dam represent industrial endurance at a national scale. They are not remarkable because they are large, but because they are always running. Their continuous operation reflects engineering discipline, long-term planning, and the understanding that some machines are too important to stop. Panama Canal, lock machinery, the mechanical system that has lifted the world's ships for over a century. The lock machinery of the Panama Canal was designed to solve a problem no previous engineering project had faced at this scale: how to raise and lower ocean-going ships safely, repeatedly, and continuously across an artificial waterway connecting two oceans. Since the canal opened in 1914, this mechanical system has operated almost without pause, lifting tens of thousands of vessels through a controlled sequence of chambers every year. At the heart of the canal are its lock chambers, gates, valves, and culverts. Ships enter a lock, massive steel gates close behind them, and water is either drained or introduced to raise or lower the vessel. This process is driven by gravity rather than pumps, using water stored in gate and lake. The machinery controlling gates and valves must operate with precision, because even minor failures can block global shipping routes. The lock gates themselves are enormous steel structures, some weighing hundreds of tons. Despite their size, they are engineered to move smoothly and reliably. Electric motors open and close the gates, while mechanical linkages ensure alignment and sealing. These components were designed for constant repetition. Many original systems operated for decades before replacement, proving the durability of early 20th century engineering. The canal cannot simply stop operating. A full shutdown disrupts international trade, delays military and commercial shipping, and causes economic ripple effects worldwide. For this reason, maintenance is performed in carefully planned stages. Individual gates, valves, or control systems are serviced while parallel locks remain active, allowing traffic to continue moving. Human operators remain central to canal operations. Crews monitor water levels, gate movements, and vessel positioning at all times. Despite modern automation, experience and coordination are critical. The margin for error is small, and every lock operation involves massive forces acting on steel, concrete, and moving ships. Over the decades, the lock machinery has been upgraded repeatedly. Control systems transitioned from manual and electromechanical designs to digital monitoring and automation. Materials were improved, motors replaced, and safety systems modernized. However, the fundamental operating principle has not changed. Water still moves ships, and machinery still controls that movement. The longevity of the Panama Canal lock machinery reflects a philosophy of infrastructure permanence. These systems were never meant to be disposable. They were built with the expectation that future generations would maintain, upgrade, and depend on them. Even with the construction of new lock systems for larger vessels, the original locks continued operating for more than a century. What makes the canal exceptional is not just its age, but its consistency. Every day, ships are lifted and lowered using the same basic mechanical process established in 1914. The machinery does not rest because global trade does not rest. Its continued operation proves that careful design, disciplined maintenance, and respect for engineering limits can keep machines working far beyond their original expectations. Tokyo Metropolitan Flood Control. Super pumps, the last resort machines that stand ready 24/7. Tokyo Metropolitan Flood Control. Super pumps form the final defensive system protecting the city from catastrophic flooding during extreme weather events. Built to operate continuously and activate instantly, these machines stand ready at all times, even when inactive because failure during a storm would result in widespread urban damage nationwide. Located beneath northern Tokyo, the underground flood control system includes massive vertical shafts, tunnels, and pump chambers engineered to redirect excess water away from rivers. The super pumps activate when rainfall overwhelms surface defenses, preventing streets, homes, transport systems, and critical infrastructure from being submerged during severe seasonal typhoon events. These pumps are not used daily, but their readiness defines their importance. They are tested, maintained, and monitored continuously to ensure instant response. Mechanical failure is unacceptable because activation occurs only during emergencies, when repair time does not exist and consequences escalate rapidly across dense urban populations, infrastructure, lives, systems. Each pump is engineered to move enormous volumes of water in minutes, not hours. Powered by high-capacity motors, the system can redirect floodwater into underground tunnels leading towards safe discharge points, protecting neighborhoods that would otherwise experience rapid and destructive inundation during seasonal storms, typhoons, prolonged rainfall, events annually nationwide. Unlike visible infrastructure, these machines remain hidden until the worst conditions arrive. This invisibility often causes the public to overlook their importance. However, engineers treat the pumps as critical life safety systems rather than optional utilities, prioritizing reliability above efficiency, cost reduction, or downtime across Tokyo's expanding metropolitan population region daily. Maintenance occurs year-round, regardless of whether the pumps are actively moving water. Components are inspected, motors tested, and backup systems verified constantly. Crews prepare for events that may never occur, understanding that preparedness itself is the system's true function within Tokyo's dense urban environment. Infrastructure, safety, planning, resilience, readiness, culture. The super pumps gained global attention after preventing large-scale flooding during major typhoons. Without intervention, water would have overwhelmed rivers and streets within minutes. Their success is measured not by visibility, but by disasters that never happen across Tokyo, suburbs, infrastructure, transport, housing, communities, lives, economy, stability, continuity, protection, security. These machines reflect a philosophy of disaster preparedness shaped by geography and history. Japan's vulnerability to extreme weather demands systems that work flawlessly under pressure. The pumps represent long-term planning where failure is considered unacceptable, regardless of cost or complexity during emergencies, storms, floods, crises, response, operations, planning, readiness, execution. Automation supports operation, but human oversight remains essential. Engineers analyze data, conduct drills, and update procedures regularly. Experience ensures rapid response when activation is required, because decision-making speed determines whether flooding is contained or allowed to spread uncontrollably across Tokyo's districts, transport, housing, infrastructure, systems, population, safety, resilience, continuity, survival. Tokyo Metropolitan Flood Control. Super pumps stand as machines defined by readiness rather than motion. They may remain silent for long periods, yet their value lies in constant preparedness. When activated, they prevent disaster. When idle, they wait, ensuring the city remains protected during extreme weather, emergencies, floods, crises events. Big Muskie Dragline. Excavator Systems, the largest land machine ever kept alive. Big Muskie was built to do one thing at a scale no other land machine had ever attempted: remove massive amounts of earth continuously in support of strip mining operations. Completed in 1969, this dragline excavator was not designed for mobility, flexibility, or short-term use. It was engineered as a permanent industrial system, intended to operate for decades while reshaping entire landscapes in Ohio's coalfields. The machine stood over 20 stories tall and weighed more than 13,000 tons. Its bucket alone weighed hundreds of tons and could remove enough material in a single pass to fill multiple rail cars. Big Muskie did not dig quickly, but it did dig relentlessly. Every movement was deliberate, slow, and controlled, prioritizing stability and endurance over speed. Big Muskie operated as part of a continuous mining system. Its role was to remove overburden, the layers of soil and rock covering coal seams. Once removed, other equipment could extract the coal below. If Big Muskie stopped, production downstream stalled. This dependency made uptime critical and shutdowns extremely costly. The machine was electrically powered, drawing energy directly from the grid through a trailing cable. This eliminated refueling downtime and allowed continuous operation. However, it also meant that power stability was essential. Electrical systems, motors, and control circuits were monitored constantly to prevent failures that could immobilize the entire structure. Maintenance on Big Muskie was not optional. It was constant. Crews inspected cables, gears, motors, and structural components while the machine remained active whenever possible. Repairs were performed at height in all weather conditions because stopping the machine entirely was avoided unless absolutely necessary. Keeping Big Muskie alive required discipline, manpower, and planning. Human operators played a central role. Automation was limited, and experience mattered. Operators controlled swing angles, bucket movement, and dumping positions while accounting for ground conditions and structural stress. A mistake could damage equipment or destabilize the excavation phase, creating safety risks and costly delays. Big Muskie's scale introduced unique challenges. Its own weight affected the ground beneath it, requiring constant monitoring of soil stability. The machine moved slowly across prepared pads, supported by massive walking mechanisms rather than tracks or wheels. Every relocation was a calculated operation involving engineers and surveyors. Despite its size and power, Big Muskie was not immortal. Changes in energy markets, environmental regulations, and mining economics eventually made operation unsustainable. In 1991, after more than 2 decades of service, the machine was shut down permanently. Dismantling followed, and much of its steel was recycled. What makes Big Muskie exceptional is not how it ended, but how long it was kept running. For years, it operated as the largest land machine ever built, maintained not because it was efficient, but because it worked. Big Muskie represents an era when machines were kept alive through effort, not replaced by convenience. Its legacy is endurance at extreme scale. CERN, Super Proton, Synchrotron, Infrastructure. The scientific machine that never truly powers down. The Super Proton Synchrotron infrastructure at CERN was designed as a permanent scientific machine rather than a single experiment. First brought online in 1976, the system was built to operate continuously as a core accelerator within CERN's research chain. While individual experiments begin and end, the infrastructure itself remains active, supporting particle physics research across generations. The Super Proton Synchrotron, commonly known as the SPS, functions as both a standalone accelerator and a feeder system for larger machines. It accelerates protons and heavy ions to high energies before transferring them to other accelerators. Because of this role, the SPS cannot simply be shut down for long periods without disrupting multiple experiments and facilities simultaneously. The machine consists of a circular accelerator ring, magnets, radio frequency cavities, power supplies, cooling systems, control rooms, and kilometers of cabling. These components operate together as an integrated system. Even when particle beams are not actively circulating, much of the infrastructure remains powered, monitored, and maintained to preserve stability and alignment. Continuous operation is essential because precision matters at microscopic scales. Magnets must maintain exact field strengths, temperatures must remain stable, and vacuum systems must operate constantly to prevent contamination inside the beam pipe. Powering down completely would introduce thermal shifts and mechanical changes that require extensive recalibration. Maintenance at the SPS follows a controlled cycle. Engineers schedule brief technical stops, but the infrastructure itself is rarely allowed to rest fully. Systems are tested, upgraded, and repaired in stages, ensuring readiness for the next experimental run. This approach minimizes risk and preserves long-term reliability. The SPS has evolved significantly since its construction. Control systems transitioned from analog panels to digital automation. Monitoring became more sophisticated, allowing real-time analysis of beam behavior and equipment health. Despite these upgrades, the core structure remains intact, reflecting an emphasis on adaptability rather than replacement. Human expertise remains central to operation. Physicists, engineers, and technicians monitor systems around the clock. They interpret data, respond to anomalies, and ensure safe operation. Automation assists, but decision-making still depends on experience and coordination across teams. The SPS also supports experiments beyond particle collisions. It provides beams for fixed-target experiments, materials research, and detector testing. This versatility increases demand for availability, reinforcing the need for continuous readiness rather than intermittent use. What makes the SPS infrastructure exceptional is not visibility, but persistence. It operates quietly beneath the surface, enabling discoveries that reshape understanding of matter and energy. Its value lies in reliability, consistency, and the ability to support future science without constant rebuilding. The CERN superproton synchrotron infrastructure demonstrates that non-stop operation is not limited to industry. In science, continuity matters just as much. The machine never truly powers down because progress itself does not pause. Its endurance ensures that knowledge continues advancing, one accelerated particle at a time.